Isomerism in coordination compounds. Two principal type of isomerism are known among coordination compounds: stereoisomerism and structural isomerism. Stereoisomerism we have done earlier also in organic chemistry, geometrical and optical. Geometrical means cis and trans. Till now we have done cis and trans, okay? Cis form and trans form. Do you know that? Remember that or not? Yes. So that's we have already done. There will be one extra now in geometrical isomerism that will be known as FACMER. FACMER. I will be talking about that. And optical isomerism will be same what we have talked about in organic chemistry. The structural isomerism again same. Linkage isomerism where linkage is different. Okay. So whatever is the name that decides the difference. Coordination isomerism where the coordination sphere is different. Coordination means complex entity is different. Ionization isomerism means the primary ion is different. So something gets into the complex and whatever is inside the complex goes out, for example. So ionization will be different. Solvate isomerism is actually similar to ionization isomerism. But in this case, it will be H2O, which will be used as ligand. Okay, H2O or any other solvent. Not tough one, easy. Geometrical isomerism, the cis and trans we have already talked about. So this type of isomerism arises in heteroleptic complexes. Obviously, it cannot arise in homoleptic because homoleptic will have all same ligands. Heteroleptic will have different types of ligands. Now understand in which type. Important examples of this behavior are found with coordination numbers 4 and 6. Coordination number 4 and 6 means there should be 4 ligands or 6 ligands. That's what coordination number is. How many ligands are connected to the central metal atom? So either 4 or 6. This is an example which you already know. Cis means the same ligands are on same side. Trans means the same ligands are on opposite side. Okay. So no difference as compared to what you have done in other chemistry in 11th grade or earlier in 12th grade. Total 4 ligands, 2 plus 2, 4. Now another one, 6, coordination number 6, also possible, cis and trans. Chlorine on same side, chlorine on opposite side. Then also it is possible. Okay. So remember here, this is the octahedral shape. So this is the horizontal. Okay. And still these are close to one another. Here on horizontal plane, these 4 are there and these chlorines are opposite. So that's why it is trans. So 4 coordination number or 6 coordination number and concept is same side or opposite side. Another type of geometrical isomerism occurs in octahedral coordination entities of type Ma3B3. So this is important one you need to remember. M is central metal, A is one type of ligand, B is another type of ligand. Total 6. But now it is not of that type, Ma2B4. So remember in previous case, it was of Ma2B4 type. Chlorine to ammonia 4. Okay. So if it is Ma2B4 type, total 6 ligands, coordination number 6, the type of geometrical isomerism will be cis and trans. So this question is asked. You will be given few configurations, Ma2B4, Ma3B3, MAB4 like that. In which one you will get cis trans? You will get in Ma2B4 or in Ma2B2. 4 coordination number, 6 coordination number, it will be Ma2B2 or Ma2B4 cis and trans. But if it is Ma3B3, there will be different type of geometrical isomerism which is known as FACMER, facial meridian. Okay, facial and meridian. I will be talking about it how. So first understand what it looks like. It will still be octahedral, but now 3 ligands will be close to one another in such a way that they will form one face of the octahedron. So you can see here, this one is forming one face of the octahedron, these three. Okay, there will be total 4 faces downward, total 4 faces upward. That's why octahedral is also known as square bipyramidal. Square bipyramidal means one pyramid topward, one pyramid downwards. So here you can see downward pyramid has this as one face. So that's why FAC. FAC is the abbreviation for facial. Another one will be here. It will form the meridian. Means the plane. It will be in the plane. So here if you see NO2, 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 these are in the plane. So in one case, they will be forming the face 3, and another case, they will be part of the plane, horizontal plane. You will be able to identify everyone. Clear that? The one which is in the meridian will be called as MER. So that's why it is known as FAC-MER isomerism. It is still geometrical isomerism because geometry is different. Now the question, why is geometrical isomerism not possible in tetrahedral complexes having 2 different types of unidentate ligands coordinated with the central metal ion? The reason for this question is, I said Ma2B2 will show cis and trans isomerism, right? Here the question is, why the geometrical isomerism is not possible in tetrahedral complexes, because this can be tetrahedral complex having 2 different types of unidentate ligands coordinated with the central metal atom. Any answer? In tetrahedral complexes, why it is not possible? The reason is because in tetrahedral, any 2 ligands will always be adjacent to each other. They cannot be opposite to each other. So in tetrahedral, if you write central metal here and you say this and these are then the plane, this is towards you and this is away from you. So say this is A, this is A, this is B, this is B. If you consider this A, all these B, A and B remaining are adjacent. None is opposite. All are at 109.5 degree. So they are adjacent. So that's why the geometrical isomerism will not be possible. You can't say they will be opposite. They will never be opposite to each other. However, in case of geometrical isomerism, 2 ligands must be opposite also to each other. So this is something I have explained. All the ligands are adjacent to one another. Optical isomerism. So remember, geometrical isomerism we talked about 2: cis trans and FAC-MER.
Sir,
Yes.
so could you please explain the FAC isomerism once again?
FAC isomerism is for facial. Can you visualize the faces, Devyansh, of Pratham, of octahedron?
Yes, sir.
Okay, so if you can visualize the faces, any one face will be formed by 3 ligands. Any one face will be formed by 3 ligands.
So how does it distinguish from MER isomerism?
In MER, those 3 will be in the plane. So this is the plane, and these 3 are part of that plane. It is square bipyramidal. So this is a square plane, one pyramid upward, one pyramid downward. Are you able to visualize the second figure as a
Yes,
square
sir.
bipyramidal? So if it is a square
Yes, sir.
bipyramidal, the horizontal middle plane has these 3. So if these 3 are part of plane, that is called meridian. If these 3 are on the faces, then facial.
Okay, sir. Got it.
For optical isomerism, you already know the concept of chirality, enantiomers, chiral, 2 chirals are enantiomers, mirror images. So non-superimposable mirror images. So I'm not repeating that one. This is part of organic chemistry we have already done. Right. The two forms are called dextro and levo depending upon the direction they rotate. Remember, D is small d, lowercase d, lowercase l, you cannot get by theory. Huh? Same thing. Okay, it is similar one. So if it is dextro levo, lowercase d, lowercase l, lowercase d means clockwise, lowercase l means anti-clockwise, and you cannot calculate it. Theoretically, it has to be done experimentally, so that's why. Optical isomerism is common in octahedral complexes involving didentate ligands. This is, you should remember. Octahedral complexes we will be talking about, mostly octahedral. It does not mean that we will not be talking about other, but mostly it will be octahedral complexes involving didentate ligands. Didentate ligands, you understand? Can you tell me any didentate ligand? Write it. Write any didentate ligand in the notebook and chat box. Write two didentate ligands. Two. Didentate ligands. Examples. Good Kavish. That is hexadentate, Tanya, not didentate. Kasak, you have written? No. Yes, no. Arna, no. Samad, no. Only Kavish has given answer here. Now, okay, good. Tanya also has given me the answer. Good. Okay. Pratham, that's only one, but yes, correct. Vedant, one, correct. Pratham, EDTA. Are you sure it is didentate? Tanishi. Tanishi, EDTA. Check. Sub, yes. Tanishi, yes. Second one now correct. Tanishi. Prakriti, yes, correct. So, oxalate, iron, and ethane 1,2-diamine. These are didentate. लिखे थे बाद में लिख लूंगा अभी हाँ अच्छा अच्छा कभी कभार से ठीक है so now this is you have En attached to cobalt and you have the mirror image of this one. Now one point where students get confused here and it is not explained in the book. You say this is mirror image and these will be chiral if these are not superimposable. You know that, okay? Non-superimposable mirror images are called enantiomers. But these look like superimposable because if you rotate this by 180 degree, it will be exactly superimposable. Huh? No, in that case, it will be achiral, right? If it is superimposable, it will be achiral, right? So basically, although it is not talked about, but few questions based on that have appeared in, I don't really remember, but in NEET or JEE, they have appeared, right? It is actually based on their internal configuration, okay? So this is not just two-dimensional. You are looking at in two dimensions. You are looking at it in two dimensions, but it is actually in three dimensions. Means this and this, these are not in this plane. These are tilted, these are at around 90 degree will be there, okay? So there will be some tilt here. Similarly here, these will be not in the plane, these will be not be in the plane. So they will repel each other. Due to that, they will not remain, they cannot remain in the plane because these electrons here in these bonds will repel. So they cannot be close to each other. So that's why due to 3D structure, they are not actually superimposable. Their mirror images are not superimposable. So this is something you need to remember that these are not superimposable due to 3D structure. In a coordination entity of the type PtCl2En2. So again, remember, it is of the type of Ma2B2 2 plus only the cis isomer shows optical activity. This is something you should remember, not the trans one, because trans one is impossible. So few points from this section specifically, I would say you will have to memorize. Otherwise, you will not be able to answer the question. Okay. So this part of chemistry, you will have to memorize that cis form. So whenever you see this form, PtCl2En2 2 plus, this form, if this is of this form, remember you have En here. But if it is in trans form, means one En has been replaced by 2Cl. That is the difference. Then in that case, cis form, this is the cis form here, will still be non-superimposable, will still be chiral. So it will show optical activity. But the trans form means these two chlorines are on opposite side. That will not be chiral. That will be superimposable. So this much you should either remember, otherwise you will forget that in this case only cis form will be chiral, will show the optical activity. So in many of the questions, there will be which one out of the following will show stereoisomerism. So trans form in many cases will not show stereoisomerism because that will be superimposable. Cis form will show stereoisomerism.
Sir,
Now, yes.
so but for being optically active, all the ligands have to be different, right? So, sir, here they are getting repeated.
Okay, now that's what I said here. The 3D structure is such that they are not superimposable. Okay, so don't get confused with what we talked about, similar to in the normal chirality. Here, due to whenever En is present, their 3D placement is very specific. Their 3D placement is very specific. Now, if you want to go into details, try to understand how. Okay, but obviously it won't be asked. It won't be asked. When you say NH2, CH2, CH2, NH2, okay. So these two hydrogens will have some placement with respect to nitrogen. This nitrogen will have some placement with respect to this hydrogen, carbon. Are you getting it what I am saying?
Yes, sir.
So the placement of these hydrogens, this nitrogen, they are different. So that's why they are not superimposable. Their internal structure is not superimposable. Getting my point?
Okay, sir.
Okay. So they are internally arranged in different manners. So that's why whenever we consider En, the answer is slightly different. You don't follow the same approach as you did in normal structures. So the cis isomer shows optical activity, not the trans isomer here. Now the question is, draw structures of geometrical isomers of FeNH3 whole twice CN4. So remember, I asked you to memorize something. You remember that? I asked you to memorize the thing. So you can identify which type of isomerism will be there. And if you can draw the structure, okay. So in one case, these NH3 will be opposite. In another case, these will be in the same direction, or you can say towards each other. So that will be cis and trans. So when NH3 will be on same side cis, when NH3 will be on opposite side trans. And as I told you, it is because of the form of Ma2B4. Also, Ma2B2 will show the cis and trans form. But remember, it is not tetrahedral, octahedral geometry we are talking about. It means there will be some other electrons as well. Next, out of the following two coordination entities, which is chiral, optically active? Tell me. Cis and trans. You have CrCl2, and remember, you will have to, I said you will have to memorize this part of chemistry. Okay, you will have to memorize this part of chemistry. So here you have cis form and here you have trans form. In cis form, you have both chlorines on one side and it is OX. In previous case, it was En when we discussed. Okay. So out of the two, cis is chiral, trans won't be. We are applying same logic. In case of En also, cis form was chiral, trans form was not. Here also cis is chiral, but OX is different. It is still didentate.